Welcome back, fellow physics enthusiasts. Today I'm going to be going over the much anticipated cross product, the second part to my vector multiplication, the one that I alluded to being a little more involved, and you will see why, probably by the length of this video. So let's just get right into it. What is the cross product? Well, it looks a little similar to what the dot product was. You are simply denoting the cross product by a cross, and that will be equal to the magnitude of A and B, vector A and B, times the sine of the angle between them. Now, the cross product is essentially just a way of determining how orthogonal its output vector is to both vectors, and orthogonal just means perpendicular to those vectors. So whatever output you receive after you perform the operation, you will end up with a vector that is perpendicular to both of them. So let's first, before I start defining all of this, I'm going to go into a little bit of a brief explanation about the basis vectors associated with the cross product and some of their various permutations. So first things first, starting with unit vectors. Unit vectors. Okay, so I'm going to be using the same notation as I did before, but just remember, keep in mind that my notation is very much the same as what you might see in other formats, like I hat or X hat. I'm going to be using the E hat notation. So E sub x cross E hat sub x is equal to some value. We're going to have E hat sub y cross E hat sub y equal to some value, and E hat sub z cross E hat sub z is equal to some value. Now, what will that value be? Well, you have two unit vectors both facing the same direction, and they will all be 0. And why is that? Well, as I mentioned, they are both facing the same direction. So because these vectors are facing the same direction, they are going to be they are going to have an angle of 0. So if they have an angle of 0, so theta equal to 0, that must mean sine of 0 equals 0, which just cancels out these other two terms, and you get A cross B equal to 0. Now, to have a little bit of a more in-depth explanation as to what unit vectors really are, they are simply just vectors with a magnitude of 1 that kind of determines the direction of the vector components. So, that being said, let's go into some of the other permutations here. So, as opposed to just basis vectors facing the same direction. So now we have to go through a few more. So before I start writing out some other permutations here, I think it's best to write out your unit vectors side by side in two pairs. And what I mean by that is take E hat sub x, comma, E hat sub y, comma, E hat sub z, comma, E hat sub x, comma, E hat sub y, comma, E hat sub z. Now, if you just write it out like this, you can fairly easily determine what your output basis vector is going to be by moving left to right and right to left. So starting from left to right, if I were to take the cross product of E sub x and E sub y, we're going to do that here, E sub x cross E hat sub y, we're going to have E hat sub z. So it's just the subsequent one in that direction from left to right. So this is just E hat sub z. Now if I were to reverse the order, go from right to left, E hat sub y cross E hat sub x, E hat sub y cross E hat sub x is equal to, well, it just goes the other direction and you land on z again. But the only difference is you incorporate a negative sign. So that is going to be equal to negative E hat sub z. So I'm not going to go through every single permutation, but I think you get the gist as to how to determine what your unit vectors are going to be. So let's get rid of this, and we're going to go through the formal algorithm the long way, and then I'll show you a quicker way to do it. So let's begin. Okay, so now we're going to define our vector components at this point and go through the algorithm and how to go about determining our cross product. Well, before we get into that, I just want to mention ahead of time that before I brought up the fact that the dot product, whenever you take that, it is commutative, which means that whenever you rearrange it, you'll output the same value regardless of the order. That is not the case for the cross product. In fact, it is a little bit of an enigma in that respect because it is anti-commutative. And what I mean by that is if you reverse the order and add a negative sign, this is the same. So that is what I mean by anti-commutative. So now that we got that out of the way, I can start breaking down our components and determining how to solve for our cross product. Okay, so let's sort of start out like we did before. We're going to break down our components like so. So let's start with vector A. Vector A is going to be AE sub hat x plus AE hat sub y plus AE hat sub z. And same thing for B. But we are taking the cross product, so that is cross B E hat sub x plus B E hat sub y plus B E hat sub z. Okay, so now we have this all written out. What I think is the best way to go about this is to distribute each and every A component into this. So by doing that, we will end up with, so A E hat sub x cross, so we're gonna have this, so our B components, E hat sub x plus B E hat sub y plus B E hat sub z. Same thing. And we are going to be adding them together here. So this cross that, so distribute this A here. So now A E hat y cross, we're gonna have B E hat sub x plus B E hat sub y plus B E hat sub z. And now, as I'm sure you've guessed, we're just adding to our next term for A. So A E hat sub z cross these components here. So B E hat sub x plus B E hat sub y plus B E hat sub z. Okay, now at this point, what we want to do is start distributing our A components across and then going about simplifying it. So what I'm going to do is I distribute these across. I'm going to put the A and B terms together and then factor out our unit vectors, and then we'll go from there. So starting with A, we're going to have, I'm going to try to move over here so you have some room to see here. So A, B, which is going to be E hat x cross E hat x plus AB, where it's going to be E hat x cross E hat y plus AB, where it's going to be E hat x plus E hat z. Now moving on to our second A component, so plus AB, where it's going to be E hat y cross, oh, I just realized that's supposed to be a cross there. My mistake. So E hat y, then E hat x. And let's move down here. I'll move out of the way in just a moment. So e hat y, e hat x, we're going to have ab with e hat y cross e hat y plus ab, where we're going to have e hat y cross e hat z. And now moving on to my second A component. So AB, so E hat Z cross E hat X plus AB. Move this over. AB, E hat Z cross E hat X, E hat Y. And then my following term here is going to be AB, and this is my final one, in fact. So AB, E hat Z cross E hat Z. Okay, all right. Now we have this all written out. Let's start making some cancellations and some simplifications. So first things first. Before, I said whenever you're resolving basis vector components, like so, it's best to write out our little sequence here. So e hat x, comma e hat y, comma e hat z, comma e hat x again, e hat y, comma e hat z. Okay, perfect. So now we can start going about this. So, like we said before, when we have the same terms, they're just gonna go to 0. So these are gonna be 0. This is going to be 0. That'll cancel to 0. Okay. Now what we want to do is clear out some space and start resolving some more of these. Okay. So we have ex by y is going to output e to the z. So just to kind of save some space here, I'm going to just be using the notation ax and ay. So I'm going to use different subscripts for that. So ax by by, ax by by is going to give us e hat z. Okay, so we got e hat z now. That one's done. So we got ab, a e to the x by e to the z, e sub z. So this time we're going backwards. So we're gonna have x, z, y. So we're gonna be subtracting now. So minus, so we have ax by bz, which is gonna give us e hat y. Okay, that one's done. So next one, ab. Now we have e sub y by e sub x. So yx, we're going backwards. So that must mean it's negative. So subtract ay by ax, or by bx, which is, like I said, e hat sub z. Okay, next one. We're moving on to this one. So e sub y by e sub z. So y, z, we're going to have a positive e sub x basis vector. So plus, we're going to have, so ay times bz, which gives us, like I said, e hat sub x. Okay, so now, next one, ab. So e sub z by e sub x. So z and x, that's going to be positive. So we're adding. So a z and bx is going to give us e to the y. So e to the y. And then that's this one here. And then our last and final one that we need here is going to be e sub z by e sub y. So e sub z, e sub z, e sub y is going backwards, right to left, so negative. Negative az by, which is e az y is e hat of x, zy x, yeah. Okay, so I think the next course of action at this point is to just simplify this and put all of our like terms together. Okay, so now we're just going to simplify some of these terms and put some of the like terms together. So at this point, our A cross B is going to be equal to, so starting with our e to the x term, we're going to have e y bz minus, so this one, minus this one, az b sub y, and that is this basis vector here. Okay, cool. So now we're going to add that to our y terms. So plus a sub z b sub x minus a sub x b sub z, and then that's e hat y plus, and then our last and final is going to be these. So plus, we're going to have a sub x b sub y, oops, did it again, minus a sub y b sub x, which is e hat sub z. And that is the cumbersome way of going about finding our cross product here. And that is this. Now, I'm sure you're probably asking yourself, is there an easier way to do that? Well, yes, there is a much simpler formal way of going about doing that, and I'm going to express that now. So let's get rid of some of this clutter and let's go about the more formal way of determining what we can. Let's go about a more formal way of determining the cross product. Okay, so as we mentioned before, the cross product is simply a resultant vector that is orthogonal to the two vectors that we are multiplying together. And it just shows you that you can determine the direction of the vector itself, the resultant vector, by using what's known as the right-hand rule. That is one way of determining at least the direction. So if you're faced with two vectors, your thumb will point in the direction of your orthogonal vector. Your index finger will be your first input value here, your first value. So A would be your index finger, then your middle finger would be B. Whichever direction they're facing, this should give you an indication as to what direction your resultant vector is facing. So that being said, we're also going to be using the essence of linear algebra here this time around. So, and what we need to define first is the determinant. And the determinant is simply just a way of computing various elements in a list that are undergoing a linear transformation. It is a scalar value, the determinant. So let's define that a little more in terms of an algorithm. So the determinant is A, B, C, and D here. Now what we want to do is we're going to multiply these two together diagonally. So A and D subtracted from the product of B and C. So that's going to be AD. Oh, I can't write my D's apparently. So AD minus BC. And that is the determinant. So this is what we're going to use for developing our cross product here. So like we did before, we are going to break down our vector components. But this time around, we're going to place them in a matrix. So to begin, you want to write out your row of unit vectors first when you're forming this matrix. So E hat sub x, E hat sub y, E hat sub z. Okay, there we go. So now we can place our vector components. So starting with ax, and then bx, ay, by, az, bz. Okay, now to use the determinant now, since we're going to be using that determinant, what we need to do is for whichever row we're trying to calculate for, we're going to cover it up and then use the determinant to determine its value. So covering up this, we are going to take a sub y multiplied by b sub z subtracted from this portion. So let me show you what that looks like. So that is going to be equal to a sub y by b sub z minus a sub z times b sub y. And then e hat sub x. This should start to look familiar here. So then we're going to add that now for our y basis vector. So covering that up, we're doing the same exact thing. So a sub x times b sub z minus a sub z times b sub z, or b sub x. And that is e hat sub y. And we are going to add that to our last final set here. So cover up our z and perform the determinant as we did before. So we are going to have a sub x by b sub y minus a sub y times b sub x. And there is our final result. So a cross b is simply just these terms. And I hope that gives you a little bit of a intuitive understanding for how to go about solving the cross product. As you can see, this was a lot simpler and required a lot less writing, and it was far less cumbersome. So that being said, I hope you were able to at least derive a little bit of value from this little demonstration here, and I hope if you have any future questions at all, don't hesitate to ask me at all. And if I made a mistake on my end, please let me know. And I will try to correct that immediately if that ends up being the case, so I don't kind of throw around false information. So that being said, I hope you have a wonderful day, and thank you for watching.